So the kinds of reactions we'll be talking about in this chapter are, well, I guess pun intended, radically different than all the reactions we've talked about. They're very really important types of reactions, and especially because radical reactions tend to happen a lot in nature without the control of any controlled by any chemists per se. Like a lot of the oxidation reactions that happen in nature by the atmospheric oxygen tend to be of radical nature. Okay. Now, I think it's really helpful for us to know what the radical molecules actually look like that we're talking about, and they look like this right here. It would be really helpful for us to know that this is actually an sp2 hybridized situation here, that carbon with the radical single unpaired electron. And can you guess what orbital that single radical electron resides in? It would be a p orbital, just like the picture shows. This is indeed a p orbital. Okay, and another thing we might notice just by looking at the simplest form of radical species, the methyl radical, it does not meet the octet, right? So meaning it's a very electron deficient species. So you can probably guess now that it'll basically react like electrophile, because it is, and also because it's electrophilic and it's a very electron deficient species, it gets stabilized by other substituents that are electron rich. For instance, let's see, if we are, let's think about this radical that's better than a methyl radical. This would be a primary radical. Okay, so I'm gonna kind of draw the structure here, and it would sort of look like that, where this is that right there is the p orbital with the unpaired electron in it. And the reason why I drew it like that is to emphasize the fact that when we have other alkyl substituents next to it, it benefits from having a phenomenon called hyperconjugation. It's not the same as conjugation because there's no pi orbitals involved per se, but what I'm showing you here, this is our sp3 orbital as well as s orbital of hydrogen. That methyl group next to the radical is, of course, sp3 hybridized, so it has an sp3 orbital that's overlapping with the s orbital of the hydrogen, right? And because the sp3 orbital has some p characteristic to it, it's actually able to do sort of a fake conjugation or overlap. So that's what we mean by hyperconjugation. So this right here is called hyperconjugation. Meaning that there's some overlap of sp3 orbital with p orbital. Okay, so this is a lot more stable than the methyl radical. Okay, and what that means then is the more adjacent sigma bonds that you have next to the radical, the better, right? So based on that, we should be able to come to a conclusion about some relative stability among different radical species. As you can guess, the methyl radical would be the worst because, well, it doesn't have any hyperconjugation whatsoever, right? But with the primary radical, there is some, so that's nice. And if you have a secondary radical, there's more hyperconjugation in this case with the two alkyl groups flanking the radical carbon there, and which is still not as good as a tertiary radical. And by now you might recognize the trend here that we've seen before, right? That this is basically the same stability trend as the cation or carbocations that we've seen. Now, here's a question for you. Do you think the tertiary radical is the most stable? Well, it turns out it actually quite isn't, because resonance capable radicals, or we could call these, do you guys remember what this is called? The position right next to the vinyl group or the alkene or double bond. It's remember, that's called the allylic group. So allylic radical would be the most stable of all because it has the resonance stabilization, right? Like so. Just as a way of review, remember that the arrows, the typical double-headed arrows we draw indicate the movement of 2 electrons, but here we're talking about 1 electron at a time. So the arrow movement or arrow depiction will look like that, with half-headed arrow depicting 1 electron. Okay. Now let's think about the sort of the most stereotypical sounds maybe confusing in the context of chemistry, but the most sort of well-known radical reaction, and that would be radical halogenation of alkanes. I think I might have told you that like alkanes are so boring that they never do anything except for like maybe combustion reaction, which is kind of important because that's how you get around with your car and stuff. But they can do another reaction, and that would be radical halogenation reaction. And here's an example that I'm showing you here, where the methyl, well, this is just methane, right, gets halogenated by a chlorine molecule. And of course this happens under some sort of special condition. Like you can't just expect methane and chlorine to mix together and then have this reaction to happen, which we'll talk about that later. The spoiler is that you need to like heat this at a really high temperature or irradiate the reagents or study materials with UV light, strong UV light, and you can cause this reaction to happen. But now, when it does happen, I just want you to know that this is not, if you look at the reaction equation, right, like this is not driven by entropy. Hopefully you can tell that because you're starting off with 2 particles and then you're ending with 2 particles, meaning it cannot be an entropy driven reaction. So this must be then driven by enthalpy, right? Just to show you that, I just want to kind of go over the thermodynamic parameters with you real quick. So here I'm listing a bond dissociation energy. I think in your textbook there's a nice table that has all these values in it. So if you're curious where I'm getting these numbers from, you can go look at those tables. But this is, for example, the sigma bond between carbon and hydrogen is worth 105 kilocalories per mole. that means you have to put that much energy into it to break apart that bond, okay? Likewise, chlorine-chlorine single bond is worth 58 kilocal per mole, and carbon-chlorine single bond is around 85 kilocal per mole. And then finally, HCl, the byproduct of halogenation, radical halogenation, or in this case, radical chlorination of a methane. The byproduct of any radical halogenation is always hydrohalic acid, in this case, hydrochloric acid. And the bond between those two is worth about 103 kilocalories per mole. And just to show you the math on this, right? Because remember, the enthalpy in the context of chemistry is usually given by the consideration of bonds that are broken and bonds that are formed. So if you add up all the bonds that are broken and subtract from that the energy that we're gaining, we're kind of compensating by the bonds being formed, we should be able to calculate the delta H of the reaction. And in this case, you'll be just for the sake of brevity and the time saving, I'm just going to skip the units here, but it's kind of like a sin in science to write numbers without units. I just want you to know. But these are the two bonds that are broken, right? The carbon-hydrogen bond and chlorine-chlorine bond. And I want you to notice how the chlorine-chlorine bond is not that strong, and that's one of the driving forces here. And the bonds that are formed, on the other hand, are fairly strong, 85 for one and 103 for the other. So you can tell that this comes out to be a negative value for enthalpy. And so this reaction is enthalpy driven, right? And that's, again, mainly coming from the fact that chlorine-chlorine bond is pretty weak, right? So that's why that's the driving force here. Now, let's think about the mechanism. And this kind of gives us an opportunity to think about like how chemists come up with mechanisms. And you can't just like pull these out of nowhere or out of your imagination. They need to be derived from an actual experimental observations. Otherwise, they're meaningless, right? So I just want you to show that to you even in this radical chlorination reaction example. Okay, when you do this radical chlorination reaction, like this reaction here, chlorinating a methane, for instance, what we notice in the experiment is that either heat or light is needed for the chlorination or halogenation to happen. And the best, if we're going to use light, the best kind of light that'll be used for the radical chlorination reaction would be the wavelength of somewhere between 400 to 500 nanometers of light radiation is most effective, and that falls in the visible light range, and it's about like a blue light as far as color goes. And interestingly, you don't have to irradiate this reaction with ton of photons or ton of light for the reaction to complete. In other words, like in doing this experiment, you can actually kind of do just emit one photon of that blue light wavelength, and that's enough to actually produce many molecules of the product. Those are kind of important experimental observations here. And so whatever the mechanism we come up with have to be consistent with these experimental observations. Okay, so first, to think about the explanation that light or heat or light is needed, okay, that might be explained by the initiation step in the mechanism, and this happens to explain the observation A and B, in that the chlorine bond has such energy level that it sort of resonates with blue light. In fact, chlorine bond absorbs blue light the best. Okay, and it is known that the chlorine chlorine bond in a chlorine molecule, the elemental chlorine, can be homolytically broken by UV light around 400 to 500 nanometer wavelength. And remember that like the energy of a light radiation can be given by this equation where h is Planck's constant and nu is the frequency. And so it's the light energy that breaks up this chlorine-chlorine bond, and hence instead of writing UV light, chemists tend to use the symbol H nu, which means light energy that breaks this up. So, and once that happens, of course, you will get two radicals, right? And this radical, I just want you to know, is the same as chlorine with 7 electrons around it. Okay. This would be an example of a free radical. Okay. This type of cleavage reaction is called a homolytic. I should say cleavage. And it's called homolytic. Remember, lysis means breakup, homo means the same. It's called homolytic because the two atoms get the same number of electrons. Usually we're used to heterolytic cleavage, right, where the two atoms separate, but like usually one atom gets 2 electrons and the other atom gets none. Those are heterolytic cleavage, but this is a homolytic cleavage that gives you a free radical. Now, this is a very rare event. Even when you shine a strong UV light, because the radicals are so high in energy, it's so unstable that this is not reaction that happens very readily. In fact, the delta H of this process is definitely positive, but once you get one chlorine radical, reaction can keep going, and that's the kind of mechanism we are proposing here, which we're going to call propagation, meaning like it only takes one chlorine radical to make many molecules of the product. Okay, so this is going to explain the observation C. And the way that must be happening is through propagation of the radical species. And what we mean by that is when this chlorine radical reacts with methane, it must be creating another radical like this. If the chlorine radical is able to abstract a hydrogen atom, right, it should be able to produce this methyl radical, and that's a propagation of radical, because even though the chlorine radical got used up in this step, we still have a very reactive radical species here, right? So this would be our propagated. Right, remember radicals are so reactive. At any given time, you really only have very few radical species molecules in your reaction mixture. Now, the common mistake that I think students make is to let this methyl radical react with a chlorine radical in the next step. But if that happened, the reaction ceases there, right? Because the radical is not being propagated. And remember that the homolytic cleavage of chlorine is a very rare event, meaning that in the reaction mixture, you should still have tons of chlorine molecules left, right? So the likely molecule that this methyl radical would react with would be a chlorine molecule, or it could react with another methane, but then the product would not be anything different. So once the methyl radical reacts with a chlorine to abstract a chlorine atom, right, like so, you end up with product molecule, but very importantly, chlorine radical is propagated, right? So this is our product, but then we have the propagated chlorine radical, and this can continue the reaction, and that's called chain reaction, because the product of the reaction is what keeps the reaction going, and that's called chain reaction, continues. Meaning that this radical can feed into this propagation mechanism as a study material. Okay, hopefully that makes sense to you. And that's how the reaction keeps going. But at the end, there's going to be eventually the end of the reaction, and that happens by some sort of a termination reaction. A termination step happens when the chlorine and the study material, I guess I should, concentration get low, right? Then what can happen is these chlorine radicals might not run into another intact methane molecule, so they might run into each other. Then you would get the chlorine molecules back. Or another thing that could happen is the methane radical might run into another chlorine radical, again because the concentration of chlorine molecule is getting low or something like that. And then again, it'll go to the product. Or another thing that could happen is the chlorine radical can eventually react with the wall of glassware. And you might wonder, well, how does that happen? Well, it's glass, so it's silicon dioxide with a silanol, like OH group on silicon that is sticking out. That's the structure, but we don't want to get distracted by that detail, so I just want you to, in a cartoon fashion, understand that like you can get a termination reaction with chlorine radical reacting with the wall, but this is what this means is, you have no more radicals, therefore the reaction terminates. But it's really important that in showing radical halogenation reaction that you show the propagation step, okay? Because otherwise the reaction doesn't work, all right? Now let's talk about the regioselectivity of this type of reaction. And that is that if you do this reaction on not just a methane, which only has one carbon, so it's kind of boring. Let's say, well, it's not that great of a structure, I guess, but if we do it on propane, right, then we can have some regioselectivity issue here, because assuming chlorination only happens once on this, it could happen at the primary carbon, or it could happen in the middle secondary carbon. So this would be a primary chloride. This would be a secondary chloride, right? And when you do this experiment, the yields are about 40% primary and about 60% secondary. Meaning there's some selectivity. It's not a great selectivity, but the secondary chloride is definitely preferred. So let's think about why we get this distribution here. And sort of one of the goals for you would be that you could actually predict these numbers, like yields, by using some thermodynamic parameters that we'll show you, okay? But first, let's think about the possibility of getting the primary chloride, right? To obtain the primary chloride, let's think about the hydrogen that the chlorine radical will have to abstract. I just want to remind you that after the initiation step where the chlorine breaks up, like so, you go through propagation step where the chlorine radical abstracts a non-radical hydrogen from alkane, like so in this propagation step. Right, that has to happen. To get to the primary chloride, we would have to abstract one of these 6 hydrogens, right? So maybe we'll say one of these 6 hydrogens abstracted by chlorine radical. Then you get to the chlorine primary chloride. So per hydrogen in propane, let's think about the yield per hydrogen. So total we got 40% of primary chloride, but that could have been due to the abstraction of any of these 6 hydrogens. So per hydrogen we have a yield of about 6.7% yield per hydrogen, right? So each primary hydrogen has like a yield of 6.7%, or you could sort of think of that as like a reactivity. It's reactivity value of 6.7%. That's now by itself it doesn't really mean anything, but relatively means a lot. So let's compare that to the relative reactivity of the secondary hydrogen, okay? So to get the secondary chloride, we would need we need the abstraction of the hydrogen to happen by the radical chloride to happen at one of these 2 hydrogens, right? So if one of those 2 gets taken by chlorine radical, then you get a secondary chloride, right? Hopefully that makes sense to you, which means per hydrogen reactivity will be 60% yield. That's 60% right there. 60% yield divided by 2 hydrogens that could have given us a secondary product. So that'll be 30% per hydrogen. Okay. What does that tell us? Relatively speaking, right, that means secondary hydrogen is, let's see, 30% divided by 6.7 is roughly 4.5. That means this is the relative selectivity for secondary. The reason why we have to consider how many secondary and primary hydrogens we have in the molecule is because the more you have hydrogens that could give you that product, right, the higher chance of that product being formed. So like we had to consider that the number of hydrogens for each type, right? So this ratio 4.5, this is the relative selectivity. Okay, what this means is that secondary hydrogen they are 4.5 times more reactive than primary hydrogens, at least in radical chlorination. Okay. So that's kind of the important conclusion we come to here. Does that make sense? And thermodynamics wise, yeah. Let's think about that. These numbers, again, I'm getting from thermodynamics data tables like before. The primary chloride case, the bond that you're breaking would be this primary carbon-hydrogen bond, which would be worth around 101 kilocal per mole. And you might wonder, well, dude, why is that different than the number we quoted earlier? But that was, remember, 105 kilocal per mole is for methane CH bond. So it's a little bit different than the primary alkane CH bond, and that's the bond that you're breaking. And then the bond that you're forming is the HCl bond, which is worth about 103 kilocal per mole. Okay, what does that mean? That means the delta H of this step, or this reaction, we could say, would be bond broken minus bond formed. So 101 minus 103 kilocal per mole, which is math even I could do, would be negative 2 kilocal per mole. So it's a little bit exothermic, this particular propagation step. Let's think about the secondary chloride case. Okay. Now, I didn't show you the mechanism here, so maybe I'll show that here. So I want you to notice how I'm showing two half-headed arrows coming from that CH bond, because CH single bond, because there's 2 electrons in there. Okay. Now, with that, let's think about this bond that's being broken, which is around 99 kilocal per mole, and the bond HCl is the same, 103 kilocal per mole. So what's the delta H at this step? Well, it would be 99 minus 103, so it would be minus 4 kilocal per mole. Meaning that this is a bit more exothermic than primary. Not by a lot, but some, right? What does that mean? That means that the secondary radical, this also tells us the secondary radical is more stable than primary radical. In fact, we can calculate the difference, right? The difference between these two would be 2 kilocalories per mole. So that's the difference. We could say that the secondary radical is about 2 kilocal per mole more stable than primary radical. Right, and we can compare these two. It's not comparing oranges to apples because we're starting with the same molecule, mind you, right? These two are the same molecules, right? And then we're letting them react with the same chlorine radical, so we can use the result to compare those two radical species. Okay, and that gives us a clue about the regioselectivity here. Now, I want to contrast that with bromination of propane real quick. Now, if we use bromine instead of bromine instead of chlorine in the same type of reaction, we also get two products: the primary bromide and the secondary bromide. But the yield distribution is very different. The secondary is about 97% yield, the primary is about 3% yield. Now, if you are the kind of person that worries, well, dude, where do you get those numbers? These are from experiments. Like some people, chemists have done this reaction, and then they weigh the product like you do with, when you do a reaction, you weigh your product. These are the yields. Okay, the secondary bromide, there was 97%, primary 30%. So there was like 30-something times more secondary product than the primary. Now, to obtain the primary product, remember, one of these 6 hydrogens need to be reacted. So, and then the total yield from one of these 6 hydrogens reacting was only 3%, right? So per hydrogen, the reactivity rating is only like 0.5% per hydrogen. To get the secondary bromide, one of these 2 hydrogens have to react. So that's a kind of a small probabilities, but yet there was a total of 97% yield for just only the probabilities of one of the 2 hydrogens reacting. So per hydrogen, the reactivity rating is 48.5% per hydrogen. So what does that tell us about the regioselectivity of bromination? Well, we can quantify that. It's 48.5% divided by 0.5%, which will be about 97 times. Now, this turned out to be the same number as the yield of secondary, which is 97. That 7%. I just want you to know that's just coincidence. Okay, those 2 numbers are not necessarily always the same. But what does this tell us? This tells us that secondary hydrogens are 97 times more reactive than the primary counterpart. I just wanted to make sure I put that circle there earlier, at least in the context of bromination, right? Like the secondary hydrogens are 97 times more reactive than primary hydrogens in bromination reaction. So that's the conclusion we can draw from this. Okay, and if you were to, now this is kind of peculiar, because if you were to compare the secondary and primary radical intermediates, radicals, the difference in energy between the 2 is still only 2 kilocalories per mole, right? The same difference. And yet, why is it that in bromination there's so much selectivity for secondary, right? This is what I'm talking about. So to get to the primary, right, product, this is what has to happen, right? The bromine radical comes in and then abstracts the primary hydrogen, and then you end up with the primary radical that will react with bromine molecule later, and that's the byproduct, right? And if you think about the thermodynamics value of CH bond, or bond dissociation energy, this is still the same as before. It's 101 kilocal per mole. And then when you think about the HBr bond, now that's a new, different bond than what we had earlier, and that is worth about 87 kilocal per mole. It's a weaker bond. That's why HBr is like a stronger acid too, by the way, which means the delta H of the reaction is, that's 101 minus 87, so like 14 kilocal per mole. meaning this is very endothermic. That's very different, right? Let's think about the secondary case, right? If that secondary hydrogen reacts or gets abstracted by the bromine radical, right? It becomes the secondary radical. We still have the same thermodynamic parameters, so this is worth, what was it, 99 kilocal per mole. Delta H here will be 99 minus 87, so that will be 12 kilocal per mole. So again, we come to the same conclusion, like 2 kilocal more stable. The stability of these two radical species, the relative stabilities haven't changed. The only thing that changed is that these reactions, kind of bromination reactions, are a little bit more endothermic. That's really the only difference, right? So that, like, if we were to draw the reaction energy coordinate diagram, right? So here's the starting material, propane and chlorine. Here's the products, at least of that step, secondary radical plus HCl. And then here's primary radical plus HCl, right? And then we know that this difference here is 2 kilocal per mole, right? And then when we're talking about bromination reaction, it's kind of the same, but we know it's endothermic, so I'm going to draw the study material down here, up here. The only thing that's different about this is we're getting HBr instead of HCl. Okay, so now why do we bother with this? Well, let's think about what the diagram will look like. For the chlorination reaction, right, the two pathways look like this. And for the bromination reaction, you know what, I'm going to use the opposite colors because chlorine kind of looks bluish, and bromine is like orange, dark orange, brown color. So those are the two reaction pathways, and remember that, like, the difference between the two products here is the same, 2 kilocal per mole. And yet the reaction energy diagram kind of looks very different at the activation energy or transition state, right? Like at the transition state, the activation energy is very small, like maybe like less than a kilocal here. So maybe but in the bromination reaction, the activation energy difference is rather large. It's about 2 kilocal per mole. What's my point? Remember Hammond's postulate that said that if two things are closer in energy, the structures kind of are similar too. And what this is saying is the chlorination's transition state, because it's exothermic, the transition state is kind of similar to the reactants, right? Like as far as energy goes. In bromination, because it's endothermic, the transition state is necessarily closer to the product than to the reactants. And that's why in an endothermic reaction, the difference in the energy between the two products really matter for the transition state, because the transition state is as different from each other as the two products are in an endothermic situation. So this is, chlorination was exothermic, bromination was endothermic. And remember the Hammond's postulate, which I wrote here as a reminder that we talked about before. The transition state is here, the closer to the reactants. So it kind of looks like this. Oops. Right, like H and Cl haven't really formed a bond very much yet, whereas in the bromination situation, the transition state looks a lot like the product. And that's why there's a larger activation energy difference between the two pathways, meaning there's more selectivity. So just to summarize here, we could say that chlorination reactions, or at least the propagation step, the delta H is negative, meaning it's exothermic, so that's a good reaction to happen. It's very reactive, but it's not very regioselective. Because it's exothermic, right? Whereas bromination propagation reaction, it was endothermic, right? Delta H was positive, and because of that, it's very regioselective. Meaning that, like, secondary product was a lot more abundant than the primary. So bromination reaction is harder to do, but when it does happen, it's selective. So synthetically, it's a lot more useful because mostly you just get one product, whereas chlorination reaction is not very as useful in synthesis because it's a really easy reaction to do, but the product is not very selective. It's kind of like if you want like a really, really worthy goal, like, I don't know, like a really hard job to get or hard goal to achieve, right? If you're really picky about where you want to end up at, like kind of like regioselectivity, if you have a really picky preference for where you want to end up in your life, the path to get there might be more of an endothermic situation. It's kind of a hard path because you have to climb all this energy to get there, but you might get to be picky about where you end up. Chlorination reaction, on the other hand, it's easy to slide down, right? Because it's always easy to slide down a hill. It doesn't take any effort, but you don't get to be very picky about where you end up. It's not a very selective reaction. And maybe there's a sermon in there somewhere.